Hi everyone, my name is Michael Hu from the National University of Singapore. Today I'll be presenting my work, Lemonshark, an asynchronous DAG-BFT protocol with early finality. This work was done with my co-authors, Alvin, Yihan, Xiang, and Jialin. So what is Lemonshark? Lemonshark is a fully asynchronous Byzantine atomic broadcast protocol with optimal resilience. Like DAG-Rider, Task, and Bullshark, it utilizes a directed acyclic graph structure to facilitate its consensus. However, Lemonshark challenges the traditional paradigm that requires leader commitment for safe results. Instead, Lemonshark is able to provide safe finalized results before leader election, reducing latency by up to 65%. So we'll begin by giving a quick crash course on how DAG-based BFT protocols work. Here we'll use Bullshark, a work that Lemonshark builds upon, as an example. In these DAG-based BFT protocols, every round, each node produces a block utilizing a reliable broadcast primitive. Each block contains transactions that carry out read or write operations on a database. Furthermore, every block references a threshold of 2f+1 blocks from the previous round. The beauty of DAG-based BFT protocols is that after a few rounds, all necessary communication is complete. The next step is to simply identify leader blocks. These leader blocks exist every few rounds and is determined either in a round-robin manner or randomly via a common coin. Here we have the red and dark red leader blocks as leader blocks. These leader blocks are elected and committed once they've obtained sufficient votes, votes that are paths from blocks in subsequent rounds. The committed leaders are then ordered totally. We can also order the causal history of our leader blocks in a similar way. So for example, the gray blocks are part of the red leader's causal history. We apply some deterministic sorting algorithm and insert them into the total order sequence. Importantly, a block's causal history excludes those blocks that were already committed by a previous leader. So therefore, only black blocks are part of the dark red leader's causal history. In Lemonshark, we say that a committed leader commits the blocks in its causal history. So that is to say the red leader committed the gray blocks upon obtaining sufficient votes. Finally, the transactions within these blocks are then executed in this total order sequence, yielding finalized results. But herein lies a problem. The arbitrary assignment of which blocks are leaders leads to blocks that are more equal than others. A leader block may enjoy optimal latencies by executing in the immediate subsequent round. However, a characteristically identical non-leader block must wait for a leader with sufficient votes to include it in its causal history in order to execute. This adds multiple rounds of latencies to our non-leader block's execution and is inherently unfair. Therefore, we ask ourselves, is it possible to obtain safe results for our transactions within a non-leader block before a leader commits them? This is what we dub as early finality and the central goal of Lemonshark. Unfortunately, as is, evaluating a non-leader block's outcome before commitment is generally not possible. I will present the intuition here, however, full proofs can be found in paper. Let us focus on the blue block produced by node 2 in round r+1. Suppose there also exist these conflicting purple and green blocks. They conflict by including transactions that will affect those in the blue block if they execute before it. To know if they actually affect the transactions in our blue block, we must look forward to the next potentially committed leader and analyze its causal history. In this scenario, the red block is a potential leader that has not yet committed. If it were to be committed, the blue block's execution will be unaffected by the green and purple blocks. However, this red leader might not actually obtain the sufficient votes to commit. We must therefore confirm its commitment, which is also incidentally the blue block's official commitment to lock in the blue block's outcome. This is necessary because if the red leader fails to get sufficient votes, another subsequent leader, which in this case, the dark red one, might create a different outcome for our blue block. So for example, its commitment will lead to the green block executing before the blue block. Therefore, safe results are only possible when we witness the leader that commits the blue block and learning it gets committed. In other words, safe results are only available when the block is committed. Without structural changes, early finality is impossible. So how does Lemonshark achieve early finality, you might ask yourself? Well, our key insight is quite simple. To determine a block B's finalized result before commitment, we just need two things. First of all, we need to know that B will eventually commit. Secondly, amongst all conflicting blocks that will commit concurrently with B, we must identify which ones will be ordered before B in the eventual execution order. Once known, we can determine B's outcome before even witnessing the leader that commits it. Lemonshark therefore makes few changes to enable this determination. The first change that Lemonshark makes is defining a specific sorting technique for causal histories. This contrasts prior works that allow any arbitrary deterministic sorting. Lemonshark sorting is nothing new. We simply use a simple breadth-first sort and then reverse the order. So in this particular case, here's a sorted causal history for block B5, which places block B2, B3, B4 after B1, simply because B1 is from an earlier round. This ordering minimizes the chance that blocks from future rounds will be ordered before blocks from an earlier round for execution. The next key change that we make is key space partitioning. Assuming transactions target specific keys, we break the key space into n distinct shards. We then make a restriction such that whenever a block is created every round, only a single node may create blocks for a particular given shard. The specific schedule is flexible as long as it's public. So in this particular case, node 1 exclusively writes to shard K2 in the round R+3, and node 4 writes to it in round R+2. This change guarantees no conflicting actions will occur within the same round. It also makes tracking inter-round conflicts achievable, even under asynchrony and Byzantine faults. Moving forward with our presentation, we'll use colors to denote a block's allocated shard. So naturally, when you do key space sharding, it introduces complexities such as cross-shard transactions. To maintain generality, Lemonshark categorizes transactions into 3 types. Alpha for intra-shard transactions, beta for cross-shard reads, but single-shard writes, and gamma for atomic multi-shard transactions that are serializable. We pick these 3 as they cover essential database operations. Other transaction types are possible, but outside of Lemonshark's current scope. In today's presentation, we'll go more in depth with type alpha transactions, while details for the rest can be found in the paper. So what does Lemonshark do? First, it utilizes Bolshar's consensus core for leader election. However, it enables each node, while having an incomplete view of the DAG, to identify, but not enforce, transactions and blocks that meet the criteria for early finality. Lemonshark evaluates early finality at the block level. We say block B meets the criteria for early finality if its block outcome, which, or the outcome of all transactions within B, after executing blocks in the sequence of B's own sorted causal history, matches the eventual outcome upon final commitment. The block outcome of B is then delivered as safe finalized results to the client. Crucially, Lemonshark is able to make this determination before B is officially committed. So now let's outline the conditions for early finality for single shard type alpha transactions. For simplicity, let's imagine a universe with only single shard transactions. Here, the green blocks all write exclusively to the same shard. We will begin with the base case and then move on inductively. Let's assume that everything prior to round R, inclusive of the green block in round R, has already been committed. Furthermore, no leaders exist in round R+2. Let us focus on the green block from R+1, highlighted by the red square. This green block possesses a unique advantage. That is, it is the first uncommitted green block. If it were to be committed by a leader from around R+3 onwards, it will be the first green block to execute. That is to say, no conflicting actions may precede it. Therefore, we can say its block outcome is safe, provided we can guarantee that it will eventually commit. To ensure that our highlighted block eventually commits, we simply check for something called persistence. A block persists in a round if out of any set of 2f+1 blocks in that round, at least one has a path to it. This happens when you have at least f+1 blocks in the subsequent round having a path to our highlighted block. By the quorum intersection property, persistence is guaranteed. When these conditions are met, we can be certain that our highlighted block's outcome is safe, and its block outcome may be delivered as safe finalized results. We can make this determination at round R+2, even though the earliest official commitment happens at round R+4. Therefore, early finality is achieved. Persistence ensures our highlighted block eventually commits. However, if we remove the assumption that no leader exists in round R+2, we cannot actually be sure that it will be the next green block that will execute. A green leader block might exist in round R+2, and it lacks a path to our highlighted block in R+1. So if this particular green leader gets sufficient votes, it would actually execute before our highlighted block. So how can we be sure that our highlighted block will be the next green block to execute? Well, Lemonshark provides two workarounds to this particular issue. The first fix is to simply check if the green block in the subsequent round has a path through our highlighted block. If the green block in the subsequent round is a leader and commits, our causal history ordering rules ensures that the highlighted block will execute first. Even if the green leader block in our round R+2 fails to commit, we simply revert back to the base case and our highlighted block will be the next one to execute. We can similarly evaluate this condition at round R+2, beating out the earliest commit time, which is in round R+3. Therefore, early finality is still achievable. We can also omit this check if R+2 is not a leader round, so therefore no leaders exist, or if the leader is predetermined to be another block, such as in the fast path of Bullshark. Our second solution is to simply wait for the green leader in R+2 to commit first. Once confirmed, our highlighted block defaults to being the next green block in line to execute, reverting back to the base case. This determination can be made at round R+3, while official commitment is at the earliest in round R+5. Therefore, early finality is still achievable. Yay. So far, we've only discussed the first uncommitted block for a shard. What about any other block? Let's illustrate an example by highlighting the green block from around R+2. Besides prior conditions, to achieve early finality, it simply needs to recursively reference green blocks from the immediate previous round, up until the last uncommitted green block, forming this chain of green blocks. This chain of recursive references ensures that any future committed leader cannot include any arbitrary subchain, and instead must include a proper prefix of this chain in its causal history. Therefore, all conflicting actions from prior rounds will eventually execute in the exact sequence as seen in our highlighted block's sorted causal history. In other words, this recursive chain captures all conflicting actions and forces future leaders to respect it. This ensures that our highlighted green block outcome will remain the same as the finalized block outcome when it's eventually committed. We can similarly make this determination at round R+3, while the earliest highlighted block may commit is at round R+4. Therefore, early finality is still possible. So those were the conditions for type alpha transactions. The interesting details for how type beta and type gamma transactions may obtain early finality can be found in the paper. For our evaluation, we forked Bullshark's asynchronous repository and implemented Lemonshark over it. We used Bullshark as our baseline since it's the state-of-the-art DAG-BFT protocol that operates in the same network asynchrony model. We also replicated Bullshark's original network and system settings and averaged results over 3 independent runs. First, we tested Lemonshark's performance when scaling the transaction load and node count in a single shard setting. As load increases past processing speed, end-to-end latencies spike due to queuing. However, consensus latencies remain stable. Overall, Lemonshark is able to enjoy 65% lower latencies when commitment latencies when compared to Bullshark. While we skipped cross-chart transactions today and its mechanisms, our data shows that even with high cross-chart activity, Lemonshark maintains at least a 25% improvement over Bullshark. Lastly, we simulated crash faults to test resilience. Typically, crash faults result in missing leaders, delaying commitment for the whole system. However, our early finality condition does not depend on leader election and still continues to produce early results. And this is after considering that missing nodes do hinder the construction of some recursively referencing chains. Even under maximal tolerable failures, Lemonshark sees about 25% improvement for single chart transactions and a 14% latency improvement under heavy cross-chart traffic. So in conclusion, Lemonshark is the first asynchronous DAG-BFT protocol to provide early finality, delivering safe, finalized results before commitment. Our paper contains full proofs, conditions for complex transactions, and an orthogonal improvement regarding pipelining dependent client transactions. Thank you for listening. I'll open myself to any questions. Yeah.